diffraction, just like what this is sample and this one is like mirror. And refraction your X-ray and show the diffraction peak just like this. This is my sample, and you can see in a different angle. This angle is 2 theta angle. You can see a lot of diffraction peak. Let me stop it. And I will show what is component in this mechanism. So this is our sample, just like this. This is our sample, powder. Why we need to use the powder? Know that? Why we need to use the powder? Because this sample is just a compound, and we need to know this compound have some crystalline or none. So the professor just teach you the sample just
okay, you can open it, yeah?
really?
No, I mean, since there was a running experiment, you can interrupt it, yeah?
Yeah.
Okay.
And this is our sample.
Okay.
And this is silicone.
Silicon.
Yeah.
Silicon powder.
Yeah, silicone powder.
Remember, this is all powder X-ray diffraction. So you can have a powder material.
Yeah. Not a single crystal, just a powder. Yeah, because
Okay,
these
go
two is
on.
different. So we use the powder to see all of this mirror we call the crystalline phase or crystalline. So for example, silicon dioxide have a 100, 200 different crystalline phase, right? So what I need to do to see all of this crystal phase, we need to use powder. So that means all of the powder is random, all of the crystalline phase is random to the outside. That means that the X-ray can reflect to this crystalline phase. So that is why we need to use the powder sample. So this is the component in this mechanism. You can see this is the X-ray source. It comes from this. This is shell and X-ray tube is inside. And this is a 1 monochromatometer. It's this. You can see right in 0.2 millimeter in this side. You can see that?
Yes, this side also.
Yeah. So X-rays come from there, and this mechanism, the X-ray source is Cooper K-hour, and is 1.54123 angstrom. And X-ray come from here and inject our sample and refract to this grating. You can see that this is the grating. Just come here and you can see the grating here. Grating. Make the line different. Did you know the grating? Don't know that?
It's like
Grit or grit?
Grating. Grating.
no, it's G in the beginning.
Grating. C, G.
Instead of C,
No.
Or
G.
Yeah,
Yeah. Grating.
I must say. Did you know the grating?
it's like it reduced the energy or something.
Detector.
No. Because you know what it is.
Yeah, it's
Yeah.
called in lambda, right?
Yeah.
That in different lambda in a different way. That is grating. Because grating is like this, and the light in, they will separate a different
different K
lambda
alpha.
in a different way.
Slide.
And
Slide.
let me show what we will need to detecting. Because we just need this, we don't want this, and use the grating
yeah, yeah.
to separate this.
I see.
And then the
It's like
detector,
It's like a filter.
Like
Yeah.
filter.
that is detector behind this. This is detector, and you can detect your diffraction key. That is grating.
And what is the difference between this and monochromator?
The monochromator is in here and here. Monochromator is make the laser beam more smaller.
Monochromatic.
Yes. And separate another
Study.
Cooper doesn't just have the K alpha. They have the K beta, K alpha 1, K alpha 2. The monochromator is just take K alpha we want to use. That is called
Yeah.
monochromator. But if the laser beam is injected in your sample, they will go into another K alpha, K beta, another side X-ray. So you need to get off way for another one. So you need to use the grating.
So grating eliminate the background from the sample, right?
Yeah. And this one is different from the downstairs one. This one is testicle top type. So if you want to move it, just move it. It's not really heavy, just 30 or 40 kilograms, not really heavy. So if you want to move it, just take it out and move somewhere. But downstairs one is not. It's very
Portable X-ray.
yeah. And let me test the
semacam itu.
silicon dioxide. Because we know the X-ray beam is just a 0.2 millimeter, it's very small. So all we need to do is make this sample in the center. So if your center have your sample, it's okay. And let the sample very flat. If the sample is not flat, the peak will be broad. Because it's just like a mirror. The mirror is not flat, your peak will be broad. So make sure your sample is flat and in the center, and that is okay.
Where is the nickel as the filter in here?
Sorry?
Cooper use nickel for the filter, yeah?
This one?
No, I mean for the filter
Filter.
of the Cooper use the nickel. And then where is the nickel in here?
Yes. Yes.
Where is?
Where is?
Where is?
Nani?
Inside. You can
In
see.
here.
Yeah, inside.
In
Oh,
in
inside.
X.
X-ray tube is inside.
Tidak.
So
Cannot see.
yeah, you can see it in this.
In the
Yeah,
inside of
yeah,
the
yeah, yeah, yeah. The nickel is after the Cooper, and this one is monochromator. And in your sample, diffraction, to the
8D
grating, and that is a
8D.
detector.
Tipenya.
Lebih gede. Kuantitasnya bagus.
And the special in this D2-PHASER is they rotate the X-ray beam and the detector. And the downstairs one, they rotate the sample one and the detector. They doesn't move the X-ray beam. So what we call a 2 theta is this theta and this theta, right? And we call it 2 theta because they rotate the sample one. So that we calculate is use the 2 theta. Okay, let's see.
Katanya sih, kalau nggak tahu. Kalau lihat sering.
Boleh tapi kalau mau pengen tahu nilainya berapa kemauannya. Tapi
Bangga kali ya. Lebih dari 100. Ngeri ya. Lebih dari
You can see I setting is start in 20 degree to theta, and it's starting in 17 or 16 to theta because they were in a negative angle and rotate to the positive angle to scan this sample. Start from 20, and this value is intensity. You can see it's 1, 2, 3. It's very small. If you have a question, just let me know.
I just know, excuse me, I just know XRD D8. And then this is D2. What's the difference? D2 and 8.
Oh, what's the difference between D2 and D8?
Yes.
It's named by BRUKER,
Yes.
so I don't know. Actually, I don't know what's
You
mean.
must check the
What's
BRUKER
mean of the
standard.
D8? But I know D2's mean. D2's mean the two thetas rotated by the X-ray beam and detector one. Let me explain it. The sample in this one, in the downstairs mechanism, they rotate this one. Sample rotate. But in this mechanism, they rotate the X-ray beam and the detector.
Oh.
They rotate these two. So they call it D2.
I think the same here.
I think the same.
Yeah, but
D8.
maybe
Yeah, that's why I say I don't know what's the
Yeah.
true meaning of the D8, but I know D2's meaning.
just
Okay,
type.
it's finished.
Just type.
You can see the very sharp peak in the 28 and 28.5 degrees is the D100 phase, crystal phase of the silicon. I use the silicon.
Just silicon.
Yeah, just silicon. You can see it. If you want to see another diffraction peak, you need to set in a stop angle to the more larger. Maybe 80. If you want to see, I can show you. All of the setting is in here. Your explosion time, your increment, you can set in here. And this mechanism just let me know what's the crystal phase or diffraction peak in this sample. So in a different lab, they have different use in this one. If I just research in a doping in some sample, so just better scans, because we just need to know they doesn't broken the crystal phase. But in other labs like us, we synthesis a new compound, so we scan very carefully because we need to know that is the different diffraction pattern in other one or between other one. So what is this diffraction peak come from is from the crystal phase, and the different crystal phase need to show by this, need to use the powder pattern because we need to let all of the crystal phase outside.
Please, please fill in this. Give it. If all have signed in, then give it back to my office. Okay.
Just absent.
By the way, this on the opposite side is my X-ray machine, but you don't explain that to you now. You can just have a look.
Okay.
From German?
This is
Yeah,
a
this
special
is from
machine
German.
for in situ X-ray. I teach you already a little bit about in situ X-ray, but please focus on this machine now.
Yes. is made by Professor Vogel. All of these components come from Germany.
It looks simple.
Not really. Not really. It's very complicated for
Of
me.
course, it looks complicated.
Yeah,
Look at this.
more complicated by this. Because this can use the in situ experiment. It can in a different temperature, but it's broken now.
It's broken now?
Yeah, it doesn't work now. I remember it can test in 400 degrees is okay.
400.
400?
Yeah. In the sample size, heating to a 400 or 500 degree, and just see a difference of the crystal phase. Because in a high temperature, the crystalline will change. You can see the phase changing in different temperature.
Wow,
Yes, that is in situ experiment.
yeah. And what happened to it? Why it's broken?
Long time.
So
I don't
old.
know that because I come here it's broken. Yeah. I don't know what is the real reason it's broken, but yeah, it's broken now.
Okay.
Yeah, did you have any question about this one?
Can we use C2 here? C2 experiment here?
What,
I mean the heating condition in C2.
No.
No?
Yeah.
You sign
Sign again.
Did you sign your name?
Oh, already.
23.
Can we see the stress group in here, Bharat?
23 to
Space group. You can because it's too simple. In a
This one is
powder enter diffraction.
Yeah.
It's just the pattern. You can calculate it by SKL. You mean? You know what I mean? If your sample is a simple compound, it's okay because it doesn't have too much diffraction peak. So you can calculate it by HKL generator. I mean cell parameter. One compound have the if it have the crystalline, it have the alpha, beta, gamma, ABC. That's it cell parameter. You can just calculate it in this pattern. But in my case, it's more complicated. Yeah, you can just use a generator to calculate what space group it is. You need to use a single crystal diffraction. Because in this case, it's just a pattern. We use a single crystal diffraction to calculate its structure, what it was, and use this structure to calculate what the pattern it was. And we just use this to confirm our result. Yeah. You know what I mean? My English is very poor, so if you don't understand, just let me know. And the special is this material is silicone and doesn't have any crystal phase, so doesn't worry about the laser beam. Just inject this material. It has any diffraction peak because this material is non-crystalline. It's non-crystalline silicone. Same as this one is non-crystalline silicone. You can see that it's not very flat, but I don't care about this. Yeah.
How you make sure it's flat? You use something to like.
Yeah, I use the glasses to just put in. Yeah.
Okay.
Same as this, but sometimes I'm very lazy. Just use something just like this and put in flat. Or okay, looks like flat and just text it because if that is not flat, that will be a very
intense.
that will not go into very broad. It will going to broad is right, but now we're going to very broad. Just this become this. You can see that different because it's very small. Or if you want to do very carefully experiment, you need to use flat. It's okay, but I don't know what's this, so just test it. That it just close to flat is okay. Any question?
About diffraction planes, 100 and 200. These two are the same, right?
No, they are not the same. 100, in this case, 100 going to there, and 200 is going to somewhere. Over the, I can show you, because diffraction is come from laser beam. I started in 25 degrees.
What is the crystallographic structure of silicium?
Silicon dioxide?
Silicon dioxide
Or what's the structure?
yes, hexagonal base.
It's hard to answer because silicon dioxide is like this. Everyone know that silicon dioxide is like this. And the structure is infinity chain in a 3D framework. You need to imagine because the solid state compound, the bonding is infinity. To make some 1D chain, 2D planar, or 3D framework. In this case, the silicon dioxide is a 3D framework. So you ask me what the structure it was. You need to draw in the computer. It's more easy to see. It's hard to explain by this board because it is a 3D structure.
So among the Bravais lattice, which one?
Or
which
Bravais
one-
lattice.
Yes, which one do you think it is?
Eye center.
Eye center,
Yeah. Yeah, the body center.
body center.
Yeah,
so
yeah.
Monoclinic, which one? Tetragonal.
Cubic.
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 Simple
Yeah,
cubic.
Wow, advanced conversation. I don't know what you have said.
And you can see this diffraction pattern. I start from 25 degree, and this one is 100. I think you can calculate it because the D spacing from 1 is lambda equal to 2d sine theta, right? The lambda is this, and you doesn't need an n. N is 1, so 1.5012 angstrom is this, and 2d you need to calculate this. The theta in here is 2 theta, so your theta is maybe 40 degree, and calculate what's the D spacing of this, right? If you know the D spacing of 100, and just this is equal to D100. Okay? And this value just put in here and you will know what the 2 theta it will exist in this pattern. Yeah, and it's very simple. It's 1 0 0 2 0 0 3 0 0. Yeah, you can see a different pattern in different diffraction peak in this pattern. But actually, silicon doesn't have a 1 0 0.